in the last video, we defined tautologies and contradictions. Remember, a tautology is a statement on its own, which is always true, and a contradiction is a statement on its own, which is always false. Today we're going to wrap up section 5.1 by talking about logical equivalence. So sometimes we can say the same statement in multiple ways when it really means the same thing. So consider the implication, if it is Sunday, then I am watching 90 Day Fiancé. This is a true implication for me. Another way of saying that is, right, well, this means as long as it's Sunday, I'm definitely going to be watching 90 Day Fiancé. And so if it's not the case that I'm watching 90 Day Fiancé, it couldn't possibly be Sunday, right? So this is equivalent to saying, if I'm not watching 90 Day Fiancé, well, it couldn't possibly be Sunday then, because every Sunday I watch 90 Day Fiancé. So it is not Sunday. Right, we would say that these two statements are logically equivalent to each other. They're asserting the same thing. As long as it's Sunday, I'm watching 90 Day Fiancé. And so if I'm not watching 90 Day Fiancé, it couldn't possibly be Sunday. This is like that very first warm-up problem, it's like the third warm-up problem in section 5.1, where I told Dennis that if you get a 90 on the final, then you'll get an A for the semester. If you didn't get an A for the semester, then you must not have gotten a 90 on the final. Right? These are two different ways of saying the same thing, so we would call these statements logically equivalent. In general, we say that two statements P and Q are going to be logically equivalent, and we denote that, it's a little bit hard to see, as P, it's like an equal sign but with 3 lines, Q, P is equivalent to Q, if they have the same truth value for every combination of truth values of the base statements. Meaning, if P is only true whenever Q is true, and vice versa. Okay, so as a real simple example, we could show that P is logically equivalent to the negation of P, right? So the negation of not P. So if P was the statement, I like Taco Bell, the negation of not P would be, it's not the case that I don't like Taco Bell, right? Double negatives cancel each other out. We can prove this using truth tables, right? So for P, it's either going to be true or false. There's no Q here. The negation of P in this case would be false and then true. And so the negation of P, well, we have to take the not P column and negate it. So we have to swap the truth values. False becomes true, true becomes false. And now if we just compare the column for P to the column for Q, or the column for not P, they have the same truth values, right? They match up. When P is true, not P is true. When Q is true, when P is false, not P is false, right? So they have the same truth values. And so we would say that these two statements are equivalent. What I was doing up here in this example, well, if it is Sunday, then I am watching 90 Day Fiancé, would be a statement of the form P implies Q. And this equivalent way of saying it, if I'm not watching 90 Day Fiancé, then it is not Sunday. That's an implication as well. And in particular, I took the conclusion over here and negated it. And I took the hypothesis and negated it, and I swapped positions. So this is P implies Q. This is not Q implies not P. We can, as an exercise, this is a good thing to try on your own, you can show that P implies Q is logically equivalent to not Q implies not P, right? We would call that the contrapositive of this implication. Okay, so let's look at a couple more examples here. Okay, well, for one thing, we had already proven, or just by the definition, we had defined that biconditional statement P if and only if Q to be the statement that's equivalent to P implies Q and Q implies P. Right, just by the way we defined it, we know that they would have the same truth table value because that was the definition of an if and only if. Okay, but we can also show that P implies Q is logically equivalent to not Q implies not P. That's the one I was talking about on the last page. And furthermore, we can prove that both of these are equivalent to the statement not P or Q. Let's do this in one big truth table. All right, let's see. What are we going to need here? I'm going to need a column for not Q and not P. Doesn't really matter the order that you put these in. True, true, false, false. True, false, true, false. The negation of P takes the P column and swaps all the truth values, so this is going to look like false, false, true, true. Similarly, the negation of Q swaps all of these, so it's going to be false, true, false, true. Okay, now I want a column for P implies Q. Let's do that first. Remember, P implies Q, this implication is only false if the hypothesis is true, but the conclusion is false. All right, and that happens in the second row. Hypothesis is true, conclusion is false. So it's true in the first row, then it's false, and whenever the hypothesis is false, the entire implication is vacuously true. So my column for P implies Q looks like this. Now let's do a column for not Q implies not P. Right, in this case, my hypothesis, the part before the arrow, is not Q. I'm just going to go ahead and label this as my hypothesis just because it's a little bit out of order here, and I want to make sure that the not Q is the hypothesis part and the not P is the conclusion part. All right, so remember, not Q is your hypothesis. Anytime the hypothesis is false, the whole implication is true. Okay, but in the second row, we have a true hypothesis and a false conclusion, because not P is true and not Q is true, not P is false. So true hypothesis, false conclusion means the whole implication is false. In the third case, again, we have a false hypothesis. A false hypothesis means the whole implication is vacuously true. And in the last case, they're both true, so the implication would be true as well. Notice now, my column for P implies Q and my column for not Q implies not P, they match up, they're identical, right? If they're identical, that means those two statements are logically equivalent. And now we can prove as well that not P or Q is logically equivalent to both of them. Let's fill in this last column here. We have not P or Q. All right, this is an or statement, so as long as at least one part of it is true, the entire or statement is true. And we're looking at the column for not P, that's here, or Q, that's here. So we're comparing these two columns, and it's an or statement. So as long as at least one is true, the whole thing's true. All right, is at least one true in the first case? Yes, because Q is true. Is at least one true in the second case? Nope, because they're both false. Is at least one true in the third case? Yep, they're both true, so at least one is true. And in the last case, yes, not P is true. Well, look, this column matches as well. You get true, false, true, true in all three cases. So because you have the same columns underneath all of these statements, that means they're logically equivalent to each other. So this is true here. All right, let's look at one last example. We're going to look at the statement, the negation of P or Q. Now, you might hope for something like this. Maybe, let's put a question mark here because I'm not sure yet, maybe this negation sort of distributes in a way, and this would be equivalent to not P or not Q. Maybe. Well, we can try and test it by building out the truth table. We've got P, we've got Q. All right, if I wanted to find a column for the negation of P or Q, then I'm going to have to start with a column for P or Q, and then I'll negate it after. So this or statement is going to be true as long as at least one of the base statements is true. So it'll be true, 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 false. And now I want to take that or statement, that disjunction, and I want to negate it. All right, so I'm going to take all the T's and switch them to F's and vice versa. So the negation of P or Q would look like false, 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 true in this truth table. Now, is this logically equivalent to the statement not P or not Q? Well, if I wanted to find that out, I would need a column for not P and a column for not Q. All right, not P is the negation of the P column, so it looks like false, false, true, true. And not Q is going to look like false, true, false, true. And so not P or not Q is going to be the disjunction of these two columns here. So it's an or statement, so as long as at least one is true, the entire or statement is true. All right, in the first case, nope, not at least one is true, so this is false. But in the second case, true. In the third case, true. And in the last case, true. All right, so are these statements logically equivalent to each other? Is the negation of P or Q, that's this column, going to give you the same column as not P or not Q? No, they are not logically equivalent to each other. Right? They're not logically equivalent in these two middle cases here, where P is true and Q is false, or vice versa. So no, these are not logically equivalent. Right? This is not going to be equivalent. All right, well, so then how do we negate an or statement? What would it mean to say it's not the case that P or Q is true? It's not the case that at least one of them is true. Well, if it's not the case that at least one of them is true, then it has to be the case that both P and Q are not true. In other words, the negation of P is true and the negation of Q is true. So let's try and build this last column here for not P and not Q, right? Because to say it's not the case that P or Q is true means they're both false. So the negation is true and the negation is true. All right, if we were to try and connect not P and not Q with an and symbol, then it's only going to be true when they're both true. All right, so in the first case, are they both true? Nope. In the second case, are they both true? Nope. In the third case, are they both true? No. In the last case, are they both true? Yes, finally. Aha! Well, now look. The negation of P or Q gives you the same column as the negation of P and the negation of Q. You get false, 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 true for both of them, which means the negation of P or Q is logically equivalent to the negation of P and the negation of Q. This is actually called De Morgan's law. And similarly, De Morgan's law also tells us that if you wanted to negate P and Q, it's going to be logically equivalent to the negation of P or the negation of Q. In other words, when you want to distribute a negation into an or statement, it swaps into an and statement, and vice versa. Right? You could prove using truth tables that this is true. It's a good exercise. But there's all sorts of different, more complicated statements that you can prove are actually logically equivalent to each other, and you can do so using truth tables like we did today.